Okay, in this section, we've been looking at line integrals over scalar functions. And our formula that we're using when we integrate a line integral for a scalar function is that it will be equal to the integral from a to b of x evaluated using our rules from our parametric equation times the magnitude of the derivative with respect to t. And one of the assumptions that we made was that the curve C be parametric, of course, and smooth. Well, let's see what it means to be smooth. For C to be smooth simply means that there will be no breaks or sharp points. Meaning that as I travel from point A to point B, there are no breaks or sharp points. Now, in line integrals, not only can we work with curves that are smooth, but we can also work with curves that are called piecewise smooth. And piecewise smooth means that overall, when I go from, say, point A, let's say I put point A here and point B is the same point, and let's say I'm going around the curve in this direction, then if I look at the curve overall, it would not be smooth since there are sharp edges in it. However, if I break this up into sections, for example, calling this piece C1, this piece C2, this piece C3, and this piece C4, then what I have is a piecewise smooth curve. In this case, the overall integral or line integral of the function will be the sum of each of the individual line integrals for the piecewise smooth sections. So we would have to integrate then over each of those curves, C1, C2, C3, and C4, and then combine them together in a sum. And this would give us the total line integral over that path. So again, what's important here is that the curve be parametric and piecewise smooth. If you look at the example that we're going to work today, we're going to work this line integral. We're going to integrate the scalar function x plus the square root of y plus z squared over a curve C, and we're going to look at piecewise smooth curves. So this curve has 3 sections to it. I've just rewritten that information here. So if you look at C1, it is the curve which looks like r of t equal to t times the unit vector k. Writing that in component form, it looks like this. Of course, remember by definition, we're going to need the magnitude of that derivative. So I found the derivative. Magnitude is the square root of each of the components squared. And we were told here that the bounds on t were between 0 and 1. So the only thing I have left to do here is to define my function in terms of x of t, y of t, and z of t. My function here, and let me go ahead and just write it as the integral, it looks like x. Now remember, when you look at the curve, r of t is defined to be x of t times the unit vector I plus y of t times the unit vector j plus z of t times the unit vector k. So we can pull the x, y, and z components directly off of our path there. So we have x, our curve is x plus square root of y plus z squared. So that's going to be 0 plus the square root of 0 plus z, which is t, quantity squared, times the magnitude of 1 with respect to t, and our bounds were given from 0 to 1. So basically, this just means that we're going to integrate from 0 to 1 t squared with respect to t. That's going to give me 1/3 t cubed, which I can look at between 0 and 1, and that looks like it's just going to give me 1/3. Okay. Our next curve was given to us as r of t equal to t times the unit vector j plus the unit vector k. And so in component form, that has component 0, t, and 1. When I take the derivative of each of the components, I get my derivative vector here, and then looking at its magnitude again, which is the square root of each of the components squared, I simply get 1. So this integral is then going to be the integral bounds on t from 0 to 1. Now we're going to rewrite our function. Remember, our function looked like x, which in this case is 0, plus the square root of y, and y in this case is t, plus 1 squared times the magnitude, which is 1 dt. That's a 1 there. So I just simply get the integral from 0 to 1 of t to the 1/2 plus 1 with respect to t. And so that's going to give me t to the 3/2 over 3/2, which I'll look at between 0 and 1, plus t, which we can look at between 0 and 1. So that's going to give me 2/3, sorry about that, times 1 to the 3/2 minus 0 to the 3/2 plus 1 minus 0, or 2/3 plus 1, which is going to give me a 5/3. And now we have our last part here, and in our last part we were told that our curve is given to us by t times unit vector I plus t times unit vector j plus unit vector k, which in component form has components t, t, and 1. Taking the derivative is the same as taking the derivative of each component, so I get 1, 1, 0. The magnitude is the square root of each of those components squared, so the magnitude is going to be the square root of 2. Now, in this case, I wasn't given my bounds directly on t. I was told that I am going from the ordered pair 0, 0, 1 to the ordered pair 1, 1, 1. Well, let's see what this means. At the ordered pair 0, 0, 1, what this says is that x will be equal to 0, y will be equal to 0, and z will be equal to 1. If I go back to my definitions here that I get from my parametric equations, I know that x is equal to t, y is equal to t, and z is equal to 1. And so setting any of these equations equal to each other, I get that t is equal to 0. Then, of course, at the ordered pair 1, 1, 1, I have x, which is equal to t, is equal to 1, y, which is equal to t, is equal to 1, and z is equal to 1, which is equal to 1. And of course, using any of those, I get t is equal to 1. So my bounds are still from 0 to 1. I just wanted you to see a different way of presenting that. So looking at our line integral, then we're going to be bound from 0 to 1. Remember, our function said that we're going to use x, which in this case is t, plus the square root of y, which will be t to the 1/2, plus z squared, which was 1, all times the magnitude, which was the square root of 2, dt. Of course, now your square root of 2 is just a value, so you can go ahead and pull that out, and then we can integrate each of these terms individually. And when we integrate t, of course, we're going to get 1/2 t squared, which we can look at between 0 and 1. And for t to the 1/2, we get t to the 3/2 over 3/2, which is the same thing as 2/3 t to the 3/2, which we'll look at between 0 and 1. And then, of course, integrating 1, we simply get t, which we can look at between 0 and 1. I ran myself out of room there. So this is going to give me the square root of 2 times, this looks like 1/2 plus 2/3 plus 1. And let's see, I think I can put those over 6. This is the square root of 2 over 6. That's going to be 3 plus 2 plus 6. So that is 11 square root of 2 over 6. So putting all three of these together, remember we had our three results from each of our piecewise smooth sections. We get then that the integral of the function x plus the square root of y plus z squared ds will be the sum of 1/3 plus 5/3 plus 11 square root of 2 over 6 1/3 and 5/3 is going to be 6/3 plus 11 square root of 2 over 6. And actually, I may want to make this a single fraction by just multiplying this by 2 over 2. And when I do that, it looks like I get 12 plus 11 square root of 2 over 6.